Assalamu alaikum students. Welcome to our final session for the course Digital Logic Design. I am Ali Roman and this session is designed for the students of BCS 3A and BCS 3D for Spring 2020 session of ComStats University Islamabad WA campus. So to start with, let us first see the contents which we will be covering in today's session. So in this session, we will be dealing with combinational programmable logic devices that are known to be the PLDs. But before that, we will be having a review of our previous class, what we have studied in our previous class. So we are at chapter number 7 of the book Digital Design with Introduction to Verilog HTL. In our previous session, what we have learned about the read-only memories, and we've seen that the read-only memories are the memories in which we can read the content of the memory, but we cannot write. But there are some specific types of memories, of read-only memories, that are programmable and that are erasable also. So we have also seen that how we can implement a combinational logic design in Rome, and last but not the least, we have seen the types of read-only memories, and we have classified those into distinct types depending upon the data access and the methodology to erase the memories. Well, today's session is the continuation of the previous session, and we can see that some of the memories are erasable and programmable, and in that context we have some specified dedicated programmable logic devices that are basically the programmable structures, and we can see that a bit similarity with the read-only memory, and we can see the functionality here, that how we can program those devices. So first of all, let us define what do we mean by the combinational PLDs or the programmable logic devices. Basically, these are the devices that are integrated circuits. Now, these integrated circuits have the speciality that they consist of programmable gates. So these gates are basically divided into two arrays. We have AND array and we've got OR array. As we can see that we can implement any Boolean function by using the min terms uh, and in the format of sum of products or sum of min terms or product of sums, but here we will follow the sum of min terms or sum of products format. So basically we can implement any function in the format of sum of products. So if we got a Boolean function in the format of sum of products, we will implement that Boolean function easily by using these programmable devices. And these devices consist of two major parts. One is the AND array and one is the OR array. Whereas the programmable ROM, the programmable read-only memory, we've got the same structure or the same arrays also there, but we've got the AND array that is fixed, which is basically constructed as a decoder, and we've got the programmable OR array. Whereas we have two other distinct structures that are programmable array logic and programmable logic array. In that particular case, the programmable array logic and programmable logic array are a bit similar to programmable ROM, but the difference here is that in programmable array logic PAL, we've got the AND array that is programmable, but we've got the fixed OR array. But in programmable logic array, that is PLA, in that particular case we've got both AND and OR arrays that are programmable. So we can summarize this with this diagram that for the combinational programmable logic devices that are distributed into three categories here. And the first category is the programmable read-only memory PROM, in which the decoder is fixed, or we can say that the AND array is fixed, whereas the OR array is programmable here in this particular case. Whereas in PAL, programmable array logic, we've got the programmable AND array, but OR array is fixed. And we can see that it's a sort of different structure or reverse structure as compared to PROM. But as far as the programmable logic array, that is much more flexible in terms of design and implementation of combinational logic modules. We've got both the array structures that are programmable. So AND array is also programmable and OR array is also programmable. So this is the difference between three architectures or three structures. So let us start with programmable logic array, PLA. If you remember that the PLA is basically a structure in which both the arrays, the AND array and OR array, are programmable. So what is the benefit of this structure is, first of all, let us see how the structure is organized and what is the benefit here. Figure 7-14 of your book basically that represents the structure in which the decoder in programmable ROM is replaced by an array of AND gate that is basically programmable. And also the input variables basically are being managed by that array that is programmable, and in order to handle those product terms, basically that AND array gives us the product terms that are available in the Boolean function. We've got the OR array that provides the interconnection between those product terms. So in order to completely implement any Boolean function, first of all, our task is to generate the product terms. Then afterwards, we have to add those, or we can say that we have to sum those product terms in the format of sum of products, so that we will use OR gates or OR arrays in order to implement that functionality. So both the arrays, the AND array and OR array, are programmable in this particular structure. Well, these sort of circuits do have another exciting feature, that is that these sorts of circuit can generate the function into its original format, or sometimes we do need the function in its complemented format, so we can also generate the output in our complemented format as well. But we will not use NOT gate here. Not if we use NOT gate, that is a fixed structure, we cannot convert that again into the original format. But here in this structure, we need a sort of mechanism that can produce the inverted version as well as the original version. So we will use basically the exclusive OR input or exclusive OR gates, and if we connect that particular exclusive OR gate with 1, basically we are generating the complement of that function or that thing, and if we connect it with 0, basically we are transferring the original function to the outputs. So these are the circuits that have two distinct features. First of all, the AND array that is programmable, that generates the product terms, and then we've got the OR array that is also programmable, that basically adds up or sums up those product terms. And then we've got the exclusive OR gate, that the main functionality of that gate is that we can generate the function in original as well as in complemented format. So can we also use minterms here? That basically depends upon the number of resources that are available here. If we've got the sufficient resources in AND array and OR array, we can implement a function in terms of sum of minterms. But due to the limited resources, we have to simplify our function, and then we have to implement that function so that our resources can be optimized here. Now let us see an example of programmable logic array, and here we can see that we've got two Boolean functions here, f1 and f2. here one in original format and one is in complemented format. We can see that this function f2 is in complemented format, and we can also see some shared elements between two function, because this is the term AC is shared between f1 and f2. Here this observation basically will save our resources. If our functions do contain some shared terms, then our resources are not wasted. We will not going to use the resources again to regenerate or to reproduce that term which is already produced in some other function. So if you see the structure of the programmable logic array here, if you see this diagram here, the implementation diagram here, since we've got three inputs here, both of the function f1 and f2 are of three inputs, a, b and c. So we are using these buffers here. These are basically the buffers. So what these buffers are doing, that these buffers are providing the input in its form as well as in complemented notation. So if we see that here this setup will produce a prime here at this line and a here at this line. Similarly, b prime and b is generated here, and c prime and c is generated here. So what we have to do is we have to generate those product terms by using these. This is basically the programmable AND array. And this setup, let me change the color of the pen here, and this setup is basically the programmable OR array, and these two gates basically are the gates that are providing the output in original as well as in complemented notation. So we've got three major units in that setup. So first of all, what we have to do is we have to generate those product terms. So here if you see that with the first gate, the term that is being produced with the first gate, that is a b prime. So if you see that this is the a line, that is the a line, and this is the b prime line. So if we see that on a crossover of these lines with this line, the fuses or the connections are intact, which means that we've got a connection of this line with this line and this line with this line. So these are physically connected, whereas rest of the connections are not connected. So the first term a into b prime is generated by the first gate. Similarly, a into c is generated with the second gate, b into c is generated by third gate, and a prime b into c prime is generated by the fourth gate. Now we've got all the product terms here. These are the product terms which we have obtained by making the connections of the AND array, programming the AND array. And now the next step is to add or sum those in order to generate a function in the format of sum of products. So we have programmed that OR array here that generates these functions. And if you see that f2 is in complemented notation, and you see that here with f2, let me first erase so that you can clearly view that. So if you see that f2 is connected with this exclusive OR gate, and the one of the input of this exclusive OR gate is set to 1, which means that here the complement of f2 is generated, the terms of f2 is generated. So f2 is being produced in such a way, whereas we don't need any complement for f1. So we have set the second input of this specified gate to 0 so that no complement is being produced. Now let us see a programming table. Basically that is a table that tells us about the terms that are present in the function, and also what are the interconnections that are required here in order to produce those terms. So if you see that we've got four product terms that are A, B prime, A, C, B into C, and A prime, B into C prime. And we've got the input variables that are basically here A is present in its original format and B is in complemented format here. Similarly, A is present in original format and C is also present in original format. Here B is present in original format and C is also present in original format. And here in this particular case, A is present in inverted format or 0 and B is also 0. C is 0 and B is 1. And here if you see that the outputs that are being defined here, so we've got the connections that are basically these are the connections that are defined here. Some of the connections are of T shaped and some of the connections are of C shaped, which you can observe from the diagram here. So F1 basically F1 consists of A, B prime, and that connection is of T shape if you observe that here. Whereas if you see A into C, A, C, this connection is also in an AND array and also in a format of C shape. Or you can say that in other words, these terms are present also in a true format or also in a complemented format as well. So the F1 function, all those terms are in their base or true format. Whereas for the C, we've got these terms that are basically there in their complemented format in order to generate F2. So we can also represent that information in the format of the tabular format, and that is basically the programmable table or programming table. We can generate that, but we can also implement these Boolean functions directly by observing that they do consist any shared terms, and first of all programming the AND array in order to generate the AND terms, product terms, and then using the OR array in order to implement the function in sum of products format. So what do we mean by the programming table which we have seen previously? It lists the product terms numerically, what are the number of product terms that are available, which we have seen in the previous table. Secondly, it specifies the required path between inputs and AND gates. So it basically tells us the requirement of how much paths are required from the input towards the AND gate so that interconnections can be made. Third important thing is, well, the third important part is that it specifies the path between the AND and OR gates. Basically, how many paths are required between the AND and OR gates. For example, the programmable structure of the OR gate, how many interconnections are required for the OR gate. And last but not the least, each output variable we may have a T or C format. T is the true format and C is the complement format. So for the programming of the exclusive OR gate. So do we need a function in a true format or do we need a function in a complemented format? Basically the function table specifies that requirement. Well, for the simplification of PLA is concerned, one important thing or one important observation which we can go through is we can carefully see that or investigate that are there any terms that are common between the functions, or we can reduce some distinct terms, product terms, because limited the number of product terms are limited the resources that of the AND array are consumed. And we do know that both of these structures have a finite number of AND gates. So in order to efficiently utilize the AND array, we see that if we have some any product terms that can be reduced or can be shared, then it would be beneficial for us. Secondly, both the true and complement of each function should be simplified to see which one can be expressed with fewer product terms and which one provides product terms that are common to other functions. So this is the important observation in order for the efficient resource utilization. If we can see that we can have some common terms so that the resources can be optimized here, and due to the limited number of resources, we have to simplify the function in order to properly implement that within the set resources. Now coming to the second example, that is example 7-2, which we've got two function 1 f1 of a, b, c and f2 basically, and have these expected main terms here, and we can see that if we can simplify those terms and arrange them in such a way that we can find out some common terms so that our resources can be optimized. So in the next step, we've simplified by using the mapping technique, and we've seen that both of the functions have some shared terms here. If you see that f1 here and f2 here, while representing the f1 into the complemented notation and f2 in the original notation here, we can see that a, b and ac, these are the two product terms that are common between both the functions. So here we can see that we can efficiently implement those terms uh, instead of implementing all the terms separately for both functions, and we can share those terms so that our implementation is simplified. So we can also simplify those functions by using the PLA table, the programming table here. So if you consider the example, the previous example here, these two functions f1 and f2, we can see that the common terms here, and so that these terms can also be observed by using the function table, and that is basically figure 7-15. These are the four product terms that are available in both functions, and we can see that these terms are common in complemented notation for the f1 and in a true notation for f2. Here you can see that these are the common terms. Well student, this is the implementation diagram for the previous example, and we can see that due to the fact that the shared element here, you can see that here are the shared terms of both functions and these are the shared terms of the both functions. Within those set resources, we have successfully implemented both functions, one in original format and one in complemented format. F2 is implemented in original format, which we can see from this fact here, and F1 is implemented in complemented notation, which we can see from this fact here. Well, that was PLA, programmable logic array. Now let us discuss the structure of programmable array logic. And we have discussed that in a programmable array logic, the OR array is fixed basically, and AND array is programmable, which we can see from this diagram also, that this OR array is fixed, and we've got this AND array that is programmable. And one important thing which we can see from this diagram, that we can reuse the function that is already been produced here in order to generate other function, because sharing of those terms or those main terms or those product terms are not allowed, which were allowed in programmable logic array. Here it is not allowed. So here what we can do is, if we can see that our functions do have some common terms, and we can share or we can replicate a function in order to generate another function, then we can do that by using these buffers. So this is figure 7-16 for a structure with 4 inputs and outputs and 3 wide and OR structure. This is basically. Well, as far as the programmable array logic is concerned, with designing with PAL, the Boolean functions must be simplified to fit into each section. And one important observation is that sharing is since not allowed here because all arrays are fixed. And if we replicate or generate any function, then we can reuse that function in order to reproduce the other function. So unlike PLA, the product terms cannot be shared among two or more OR gates. Therefore, each function can be simplified by itself without regard of the common product terms. And as far as the output terminals are concerned, the output terminals are sometimes driven by three-state buffers or inverters, which we can see from the next diagram of the implementation of an example. For example, here we can see that we've got four functions of four variables or four literals A, B, and C, D, and functions are W, X, Y, and Z that have some specified terms here, and we can see that some of the functions, for example, W function consists of 2, 12, and 13, which we can see that this function can be replicated by implementing the Z function here. So first of all, let us simplify W, X, Y, and Z. This is Y and Z. Which we can say that Z can be represented as W plus these two terms. Now let us see the function table here, and we can see the outputs of W, X, Y, and Z, and these are the resource terms basically that implement those terms here. Since we've got the fixed structure of AND gates, so this is the first structure, then the second structure, and third and fourth structure. And we can see from this diagram here, and these are the respective minterms. That we are basically reusing the W here in order to produce Z here. So what we will do here, that we have to use W in its original format, so we will make basically here an interconnection so that we can use those terms in order to produce Z. So student, that was all for today's session. I hope so you will be able to now understand the concept of programmable logic arrays and programmable array logics, and you will be able to implement any Boolean function by either using programmable logic arrays or programmable array logic.